Actually, Aniket has new papers, and also actually one of the papers just accepted this week.
Yeah.
But Aniket already gave a couple of talks already, so he feels uncomfortable. So he can talk about his earlier work 2 years ago. Yeah. So that is the generation, possible generation of the gravitational waves from some tensor aggravation. So. And as I said, please remain in his talk. After his talk, we're going to have Q&A. Yeah. Okay, so today, I need to talk about probing the early universe with gravitational waves. Yeah, let's welcome.
Okay, so thank you, Keiichi, for the introduction, and I would also like to thank Tepe and the other European Committee members for allowing me to give this talk at such short notice. So today I want to talk about how we can use gravitational waves to probe the early universe. So this is actually the very early universe, so the era of inflation. So let's just dive right in and ask, why do we care to observe gravitational waves from such a time? So I'm sure most of you have seen this map before. So this is the map of the CMB temperature fluctuations from the Planck collaboration. So what this map shows is that all these points represent the temperature fluctuations of the cosmic microwave background. So the way we measure this is we go out, we measure the CMB temperature at different points in the sky, and for each point we subtract the mean value over the whole sky. So these temperature differences are plotted here, and the blue points are slightly colder than the average CMB temperature over the whole sky, and the red points denote points which are slightly hotter than the average temperature of the sky. Well, what is really cool in this map is that these temperature differences that I'm talking about are actually of microkelvin level. So what we see is how fine we can observe even temperature differences of microkelvin orders. And this actually represents the density fluctuations in our universe that were already present at the time of recombination, which is where we get the cosmic microwave background from. So using this map, or the equivalent power spectrum map, which is also I'm sure you've seen many times before, we can learn something about the physics of the early universe. So some questions that are of interest. Before that, so given this, why then do we care about gravitational waves? Well, as I already said, the CMB comes to us from the point of recombination, which is already when the universe is about 400,000 years old. So for any physics that comes before that, because the universe was a hot, dense plasma of electrons and ions, it was totally opaque to electromagnetic radiation. So no photons would escape from that era and come to us. Therefore, the CMB, or this age of 400,000 years old, is the first time that we can receive any light. Therefore, in order to get any information about physics which happens before this era, we need some other carrier. And gravitational waves are one such carrier, the other being cosmic neutrinos. So gravitational waves, they are not strongly coupled to any species that are present in the early universe, and so they can propagate to us right from the beginning of our universe. So what kind of information are we interested in? So as cosmologists, the primary questions of interest to us are things like how old our universe is, what is it made of, how does it evolve over time, maybe what is its eventual fate, and also how did it all begin. So this part, the beginning, is what I want to talk about today. So to start with, let's talk about inflation. So inflation is a period of accelerated expansion of space in the first 10 to the minus 36 seconds of the universe. And it is also common to assume that the Hubble rate during inflation, which is just the rate at which the scale factor changes, is approximately constant during this time. As a result of this, we see that the scale factor, which is basically a measure of the difference of the distance between any 2 points, grows exponentially during this time. So this is shown here by this exponential, roughly exponential growth of the distance between any 2 points. Now, in principle, there are many different arguments from an observational perspective why we need a theory of inflation and why we need an accelerated expansion of space, right, to see the super horizon or to see the large-scale structure that we see in the CMB. But for today's talk, the most important and the most appealing feature of inflation is that it provides us a natural mechanism to explain these perturbations that we see. So once you have an initial perturbation, we know that it can grow by gravitational instability. So regions that are overdense can accrete matter and become more overdense, and regions that are underdense lose matter and they become more underdense. So once you have a perturbation, it can grow by gravitational instability. But how do we actually get the initial perturbations? So the answer that inflation provides is quantum fluctuations. So to see how that exactly works out, let me first talk about a more familiar case, I hope, which is fluctuations of the electromagnetic field. So I guess fluctuations of the electromagnetic field, I guess we're all very familiar with those. They are just electromagnetic waves or photons. So in flat empty space-time, they obey the Maxwell's equation with a zero source. So the equation is basically box of A nu, which is A nu is the vector potential for electromagnetic waves, and that is equal to 0. So as you can see, this equation is linear in this A nu, which essentially represents that photons do not interact with each other. So there is no interaction terms. So we can expand, to try and solve this equation, we can expand A nu as a sum of plane waves, which is shown here. So this is just a Fourier expansion. Then if we put this back in here, we find that for each Fourier mode, this equation holds. Now this is a familiar equation, right? This equation just represents harmonic oscillators. So what we have done and what we see is that the electromagnetic wave is just a sum of different harmonic oscillators, each oscillating with a different frequency, which is proportional to k. So then, in order to go from here, which is this classical fluctuation theory, to quantum fluctuations, we just need to make a small step. So we already know how to quantize a harmonic oscillator. So what we can do is we simply replace each of these harmonic oscillators with a quantum mechanical operator, and we require that canonical commutation relations hold for this operator. And once we do that, the electromagnetic field becomes quantized, and the quantum mechanical electrodynamic field is just a collection of independent harmonic oscillators, each of which is a quantum object. So what this tells us, and what we also know from our studies, I guess, before, is that even in empty space where there are no sources, the electromagnetic field has these quantum fluctuations or these vacuum fluctuations which have non-zero energy. And there are some indications that you can probe this or test whether or not this exists using the Casimir effect. But at any rate, these quantum fluctuations are an inevitable consequence of the quantum mechanical behavior of the electromagnetic field. So now let's examine what happens for the gravitational field. So in general relativity, we all know that gravity is not a field per se, but it is just described by this space-time metric, G mu nu. So this is a 4x4 symmetric matrix, and once we apply all the gauge constraints on the theory to state essentially that the theory should be independent of all the coordinates of any choice of coordinate, we are essentially left with two transverse traceless components of just the spatial part of this metric, and these are the two gravitational wave polarizations that we are all familiar with. So one is this plus polarization, which causes this kind of a distortion, for a ring of particles, and the other one is the cross-polarization, which causes this kind of a distortion. So we can also consider linear combinations of these, the left-handed circular polarization and the right-handed circular polarization, just as in the case of electromagnetic waves, and I will use those later on in the talk. So okay, so this is so we have two polarizations of gravitational waves, and let us now consider the inflationary era. But we assume that the space-time is totally empty. There are no sources, except for the fact that the space-time is expanding during inflation. So there is this exponential expansion happening. And otherwise, it's homogeneous, except for maybe some slight perturbations around this homogeneous background. So in that case, the spatial part of the metric can be written like this. So delta ij is just the homogeneous background, and hij is any small perturbation that can happen during this time. Then if we add to this the Einstein equation for gravity, it just says that in empty space-time, the Einstein tensor should be equal to 0, so there are no sources. Then we get the following equation for the gravitational waves. So now let's try and make an analogy with the electromagnetic case. So we saw earlier that Maxwell's equations in empty space-time give the following equation. These we quantized, this we wrote as a sum of harmonic oscillators, and we quantized each of these harmonic oscillators to get the quantum mechanical description of electromagnetic fields. In analogy, we have the same equation now for gravitational waves. So what if we do the same procedure here? We can also expand this equation in Fourier components, and then we can call this a sum of harmonic oscillators and try and quantize each of these harmonic oscillators. So if gravity is quantized, we should be able to see such a description, and these fluctuations of the gravitational field should propagate towards us as gravitational waves. But there is one problem. We don't actually see these vacuum fluctuations for the electromagnetic field. So what enables us to see, or maybe hope that we can see these quantum fluctuations of the gravitational field? Well, the answer turns out to be inflation. So I show here the evolution of the amplitude of a particular gravitational wave with, let's say, a wave number k and the wavelength given by the inverse of k as a function of time. This dashed line here shows, for want of a better word, roughly the Jeans scale for this gravitational wave. So what inflation enables is this decrease in the Jeans scale. So once again, in fluid dynamics, the Jeans scale corresponds to this particular length scale below which the fluctuation does not grow, but beyond which the fluctuation can actually grow. Now in the era of inflation, the role is a bit changed. So below the Jeans scale, the fluctuation actually just damps because it is a vacuum fluctuation. So it gets excited and then quickly gets damped. But once it exceeds the Jeans scale, it becomes constant. So what inflation does is creates this decreasing part of this Jeans scale, which allows fluctuations to exit the horizon at some point. And once they exit the horizon, their amplitude becomes frozen. And then later on, once we have the standard Big Bang with radiation domination and matter domination, the Jeans scale starts increasing once again, and these fluctuations can re-enter the horizon, and then they can actually seed structure, for instance, in case of scalar fields or primordial gravitational waves that we can then observe. So, okay, so all this is fine. Maybe we can actually see these gravitational waves. So let's say we go out and we try and look for these gravitational waves. How can we make sure that they are actually coming from quantum fluctuations and not from some other astrophysical process? Well, once again, there is another piece of quantum mechanics that we can use. So we know that in the ground state, the harmonic oscillator, a quantum mechanical harmonic oscillator, as a Gaussian wave function. What this means is that the displacement obeys a Gaussian distribution. And we already saw that we can express the gravitational wave as a sum of these different harmonic oscillators. So if these are all fluctuating in their ground state, each of these has an amplitude that is Gaussian distributed. And because the whole wave is just the sum of these independent Gaussian variables, the total distribution of the amplitude of the gravitational wave should itself be a Gaussian. So this just follows from statistics. Thus, if we can somehow if we can somehow conclude that the amplitude of these gravitational waves is Gaussian, we can prove that they arise from quantum fluctuations, and that will then be a proof for the quantum nature of gravity. But there's one catch in this story. So I have assumed that all these are independent. And because of this independence, once they are summed over, the total distribution becomes Gaussian. But if there are some interactions among these oscillators, or they start interacting with some other field, they are no longer Gaussian, and then the total sum is no longer Gaussian. Thus, non-Gaussianity can actually probe interactions of these fields that are present during the time of inflation. So once again, we are talking about the first 10 to the minus 36 seconds of our universe. So, okay. So once we have that, let's see how we actually go about measuring something like this in the CMB. So all these primordial gravitational waves, they produce a special polarization in the CMB. So earlier, or even this represents the temperature fluctuations of the CMB. We can make an analogous map for the polarization of the CMB, and in particular look for the pattern of the polarization, which is called the B-mode polarization, and that should also look something like this. And that is exclusively sourced by tensor or by primordial gravitational waves. So then, if we want to test for Gaussianity, we know that the Gaussian distribution is completely characterized by these two moments, the mean and the variance, well, the standard deviation in this case. So, because all these fluctuations originate from quantum mechanical fluctuations, the mean should be 0, but the variance is not 0, and you can actually measure that by measuring something called the two-point function, which is just that you cross-correlate the value of the field at this point with the value of the field at another point. And this is a function of the separation between these 2 points. Equivalently, we can think of the Fourier transform of this measurement, which is just the power spectrum. So that is what is shown here. So this is for the temperature fluctuations as a function of the separation between these 2 points on the sky. Okay, so what does that power spectrum actually look like for vacuum fluctuations? So yeah, you can do all that, you quantize the gravitational field and you solve the equations, and you eventually end up with something like this. So this is the power spectrum, which is just the amplitude of the fluctuation or the amplitude of the gravitational wave as a function of its wave number. So the two most important things to note here are that the first one is that this power spectrum is parity invariant, which means that both the left and the right-handed polarizations of gravitational waves are equally excited. And this is kind of expected because we do not expect vacuum fluctuations to have any preference for any particular polarization. And the second thing to note is that aside from this factor of 1 by k cubed, they are scale invariant, and they depend only on the hover rate during inflation. So what this means is that gravitational waves of all frequencies should have the same amplitude except for this factor of 1 by k cubed. So this is the story for vacuum fluctuations, but we should also recall that the Einstein's equation is actually a nonlinear equation. So the Einstein tensor, for instance, goes roughly as the square of the metric tensor, and therefore the equation is not just linear equation, as is the case for electromagnetism, but it is actually a nonlinear equation. That means that these gravitational waves must also, in fact, be non-Gaussian, because we just saw that if the equation is linear, we have Gaussian fluctuations, but if it is non-linear, we have non-Gaussian fluctuations. So in fact, if we do the same analysis, but now we expand this equation to second order in these fluctuations, we get this very complicated expression. The key point being that the right-hand side is no longer zero, and we have gravitational waves which are sourced by interactions among other gravitational waves. So now, okay, so how do we actually go about then measuring this non-Gaussianity? So for a Gaussian distribution, once again, we can only characterize it using the two variables, the mean and the dispersion, or the power spectrum. But for a non-Gaussian distribution, we can have an infinite number of possibilities. You know, the third moment can be non-zero, the skewness, the kurtosis, and all the higher order moments, any of them can be non-zero. So this is a bit of a non-trivial problem. So here I focus on just the first of this whole hierarchy, which is the bispectrum or the 3-point function. So the 3-point function is simply defined as the cross correlation between field values at 3 points x1, x2, and x3, and it's written like this, let's say. And then the Fourier transform of this 3-point correlation function becomes the bispectrum. So what this equation also shows is that this bispectrum is only non-zero when these 3 wave vectors sum up to 0. So they make a closed triangle. And then the way to characterize this bispectrum is by looking at the shape of this closed triangle. So for instance, there are like 6 shapes denoted here, 5, and then there is a continuum of shapes here. But for instance, you can have this kind of a shape, which we call a squeezed triangle, and this represents interactions between 2 very short wavelength modes in the presence of one very long wavelength mode. So this kind of interaction is very it's very symbolic of self-interactions of a field. And then different kinds of interactions have their own different shapes for the bispectrum, and which shape actually is observed then tells us something about what kind of interactions are taking place. So for vacuum fluctuations, once again, as I just showed, they can have self-interactions because of the non-linearity inherent in the theory. We would expect a shape like this to show up. So one last bit of formalism before we go see some actual results. So because this is a closed triangle, we can totally describe it using the 3 lengths here. So the 3 lengths are K1, K2, K3 corresponding to the 3 momenta or the 3 wave numbers of the gravitational waves that are interacting with each other. And we can quite generally arrange them in this order such that K1 is greater than or equal to K2, which is greater than or equal to K3. And then for fields that have a scale invariant power spectrum, so which is also true for the vacuum fluctuations, it turns out that the bispectrum itself does not depend on the exact values of these wave numbers, but is only a function of their ratios. So for instance, it would only depend on R2, which is the ratio of K2 to K1, and R3, which is the ratio of K3 to K1, and we can generally set K1 to 1. So with all that, let me now show what the bispectrum looks like from vacuum fluctuations. So here I show the bispectrum of 3 right-handed gravitons that interact with each other, scaled by some arbitrary factor, which I will talk about later, as a function of R2, which is one of the wave numbers, and R3, which is the other wave number, and the last one we've already set to 1. So what we see as expected is that it peaks at this location where one of the wave numbers is much shorter than the other 2, and that is exactly the squeezed configuration we saw before. So that is in fact coming from the self-interaction of these gravitational waves. Now, this whole picture is fine, but what about if we want just one number to characterize how non-Gaussian these gravitational waves are? So we can do that using this particular ratio, which essentially represents the skewness of the distribution of gravitational wave amplitudes divided by the square of their variance. So a number that is very high gives you a very highly non-Gaussian distribution, and a number that is close to 0 gives at least a distribution that is not skewed. So for this particular case, for vacuum fluctuations, we find that this is about 3.6. So it's of order unity. So just to also emphasize the polarization part, here I show the cross bispectrum. So we have 2 right-handed gravitons and 1 left-handed graviton, and these interact with each other. Now, naively, we would not expect a left-handed and a right-handed graviton to interact with each other. So that is actually shown here. So when you have, so the left-handed graviton in this case has the wavelength 1, so it's the shortest flow, and R3 controls the wavelength. No, one of the right-handed gravitons is the smallest one, and R3 controls the wavelength of the left-handed graviton or gravitational wave. So we see that this bispectrum actually peaks in the limit that the left-handed gravitational wave has a very long wavelength. So what that means is that this is just showing the interaction of 2 short wavelength right-handed gravitational waves in the presence of 1 very long wavelength left-handed gravitational wave. So having seen all of this, it is natural to ask, have we actually seen these gravitational waves from vacuum fluctuations? Or what do we actually need to do to observe them? So maybe you guys remember there was this whole press release for the BICEP 2 results in 2015 where they claimed to have detected gravitational waves from vacuum fluctuations, which later turned out to be just dust. So what we actually need to do is to just go through this checklist here. So the first thing we need to check is that the gravitational waves that we are looking at, or the B-mode power spectrum, is consistent with the scale invariant power spectrum. What that means is that you should see a non-zero B-mode power in different frequency channels. So for the BICEP case, they only saw this for 2 frequency channels, which is not enough to conclude that it is actually coming from primordial gravitational waves. The other thing we need to check is that the gravitational waves are actually parity invariant. So this you can check by looking at, I didn't talk about this but you can do this by looking at the cross correlations between the temperature and polarization of the CMB. And lastly, we need to check that the bispectrum of these gravitational waves is also consistent with a Gaussian distribution, or an almost Gaussian distribution. So now coming to the one slide that I have on observations. Have we actually seen these gravitational waves? So the answer is unfortunately no. And this is, I think, the current state of the art. So the same story that I just told about these gravitational waves being pulled out of the horizon and staying frozen, you can also say the same thing about scalar fluctuations. So these are just density fluctuations, if you wish. And these leave their imprint in the temperature fluctuations of the CMB. And these have been shown to be super-horizon, and they have also been shown to be adiabatic, which is one other very robust prediction of inflation theory. We've also found that they are very close to Gaussian, with almost no non-Gaussianity, and they have been shown to be almost scale independent. So NS is just a number which characterizes how these, what's the tilt of these power spectrum with respect to K. So NS equal to 1 is exactly scale independent, and NS is found to be roughly 0.96, which is exactly the prediction from inflationary theory. The one last prediction of inflationary theory is the existence of these vacuum gravitational waves, and we have still not detected those. what we have is from a non-detection only an upper limit to the amplitude of these gravitational waves with respect to the scalar fluctuations, and that is bounded from above by about 6%. So these vacuum fluctuations are a robust prediction that we actually need to see before we can say that, you know, all this story of quantum fluctuations getting stretched and then eventually seeding structure is true. Okay, so now this is all the story for vacuum fluctuations. Until now we haven't assumed anything about what kind of fields or particles are present during inflation. But maybe let's now try and fix that with the help of an illustrative model. So let's say we have inflation and the universe is expanding at this exponential rate. So the gravity, once again, we consider is described by GR, and phi is now a scalar field, which is called the inflaton field. And this scalar field is the field that is responsible for driving inflation. And we also consider that this scalar field is also the one that generates all the scalar perturbations or all the density perturbations, which eventually seed the present day matter in the universe. So in addition, let's suppose that there is also an axion present during inflation. Now axions are one of the most promising candidates for dark matter, and they're also needed to solve the strong CP problem in QCD. So they might also have existed during inflation. And let's consider that this axion has an energy density which is very small compared to that of the inflaton, so that it does not affect the background evolution. So as the universe inflates, both the inflaton and the axion slowly roll down their potentials. But once you have an axion, it naturally couples to gauge fields. So this coupling naturally appears. And what that does is that as the inflaton rolls down, because of this coupling, it dumps some energy into these gauge fields. So in particular, for this case, we consider SU2 gauge fields. And these, the important feature of this particular group of gauge fields, so these are gauge fields are like the V, W, and Z bosons in standard particle physics. And the important feature of these fields is that they have a tensor degree of freedom. So what that means is that as the axion rolls down, it can also excite this tensor degree of freedom of the SU2 gauge field. And then that can linearly source gravitational waves. So once again, the right-hand side is non-zero, but this is already appearing at linear order and no longer at second order. So in order to understand a little more in detail what happens, here is a plot showing the amplitude of the gravitational wave, which is denoted as SAR, and the amplitude of this gauge field, the tensor part of this gauge field, which is denoted by T. So this line denotes the horizon crossing. So this is the point at which the amplitude, at which the gravitational wave or this gauge field exits the horizon, and its amplitude becomes frozen. Far to the right is when these fluctuations are still deep inside. Excuse me. When these fluctuations are still deep inside the horizon, and so they are just getting excited and they decay as the universe expands. But however, the axion is still rolling down, and what it does, it pumps energy into this gauge field. So that gets amplified, and once it crosses the horizon, this transference of energy between the axion and the gauge field becomes inefficient, and it quickly decays until it freezes over once it has become quite super horizon. Whereas these fluctuations, these tensor fluctuations, they then source these gravitational waves. So that you can also see here in this plot, in this line, which also gets amplified right before horizon crossing and then gets frozen.
Sorry, so the potential of axion here is like something you arbitrarily choose?
It's just a cosine potential, which is the standard potential we use for inflation. So, right. So now we have these two kinds of gravitational waves. One are the ones that are produced by a mechanism like this, so some gauge field sourcing gravitational waves, or the vacuum gravitational waves. So we need something to distinguish these two kinds of gravitational waves. So one is the amplitude. So let's take a look at what controls the amplitude of these gravitational waves. So once again, there are two processes that lead to the amplification of these gravitational waves. First, the gauge field gets excited, so gets amplified by its coupling to the axion, and then it transfers its energy to the gravitational wave. So the first process is controlled, the efficiency of this first process where the axion transfers energy to the gauge field is controlled by the strength of the coupling between the axion and the gauge field. So that is encoded in this parameter NQ, which essentially is just some coupling strength between the axion and the gauge field. And we see that there is a near exponential amplification of the gauge field depending on this coupling strength with the axion. And then once you have this gauge field, some energy in this tensor part of the gauge field, general relativity tells us that this can lead to a curvature of space-time or gravitational waves, depending on what its energy density is. So that is controlled by this parameter epsilon b. So the larger epsilon b is the more is the amplification of the gravitational wave. Okay, so but just with the amplitude, you cannot really distinguish where the gravitational wave is coming from, because a higher amplitude gravitational wave might equally well come from an inflationary era with a larger Hubble rate. So we can go and look at the power spectrum and how it varies as a function of wave number. So that is shown in this plot. So please just focus on the blue line here, which shows the power spectrum of the sourced gravitational waves. So these are gravitational waves sourced by the gauge field. And this is shown as a function of the wave number, the log of the wave number. And CMB typically probes scales below roughly 15. So what we see from this plot is that even for the sourced gravitational waves on the scales probed by the CMB, we have an almost scale-independent power spectrum. So this is exactly the same as for vacuum fluctuations. So even with this, looking at the spectrum of the gravitational waves, we cannot say anything about their origin. However, what is also interesting is that by controlling these two parameters, epsilon b and mq, we can also make these gravitational waves red tilted or blue tilted. So red tilted or blue tilted. So if we actually observe such a tilt in gravitational waves, we may attribute it to a mechanism like this. So okay, so just the power spectrum is not sufficient to tell us about the origin of these gravitational waves. So then we go to the next higher order statistic, which is the bispectrum. So for this particular scenario, the bispectrum is actually sourced at the most significant level by these three kinds of interactions. So once again, psi is three gravitational waves, and we want to consider what kind of interactions they can have. So we see that one kind of interaction is where they interact with each other via the self-interactions of the gauge field. So this SU2 gauge field is a non-abelian gauge field. So that can have self-interactions in contrast to, say, electromagnetism, where photons cannot interact among themselves. The other kind of interaction is where one of these gravitational waves interacts with the other ones by exchanging just a couple of these gauge bosons. And the last one is where it actually decays into a gauge boson and a gravitational wave, and that then decays further into a gauge boson. So just to get an idea of which one of these is actually the most dominant diagram, we once again consider this exponential amplification. So the gauge field is exponentially amplified. So naively, we would expect that the larger the number of gauge bosons that are exchanged in any process, the higher is the contribution of that particular interaction. So in this case, that would mean that this diagram, which has 3 gauge bosons being exchanged, is the more dominant one with respect to these other 2 which have only 2 gauge bosons. But we're not looking at the interactions of gauge bosons. We're looking at the interactions of gravitational waves. So we also need to consider this particular vortex, which accounts for the transfer of energy from this gauge boson to the gravitational wave. And this is proportional to the energy density of this gauge field, and which is, as I said, is very low. So it turns out that eventually this diagram and this diagram, which has one lesser of these vertices, are actually roughly the same order. Whereas this diagram, which has only 2 gauge bosons and all 3 vertices of this kind, is extremely subdominant compared to these other 2. So then we can calculate what the shape of the bispectrum looks like, and this is what I showed here. So this is once again the gravitational wave bispectrum of 3 right-handed gravitational waves for the model that I just described. So gravitational waves being sourced by some gauge field. And now let us contrast this with what we have from the vacuum fluctuations. So as you can see clearly, if we can measure this bispectrum, we can clearly distinguish which one, what the source of these gravitational waves is. So this diagram peaks in the squeezed limit, whereas this one peaks roughly somewhere here, which corresponds to these 2 wave numbers being slightly lower, so that means their wavelengths are slightly larger than the third gravitational wave. So in summary, I hope I've shown or I convinced you that gravitational waves that are produced by sources such as gauge fields can be scale invariant, can have also rected or looped in their power spectrum. They are also chiral, so this isn't something I described explicitly, but essentially because these gravitational waves are sourced by the axion, which is a pseudoscalar, so that violates parity, and as such only one particular polarization of the gravitational waves is excited here. So either the left-handed or the right-handed polarization, whereas the other one stays in its vacuum state. And lastly, these gravitational waves are also non-Gaussian, and we would like to now characterize how non-Gaussian these are compared to, say, the vacuum fluctuations. So this is shown roughly in this plot, but what is important is, I guess, just this equation, which once again looks at the ratio of the skewness of these gravitational wave amplitudes with respect to the square of their variance, and this is inversely proportional to the energy density of these gauge fields, roughly. So this energy density once again can be very low, so it can be like 10 to the minus 6. What that means is that this number can be as large as 1 million for these gravitational waves that are sourced by great gauge fields. And this is definitely very much more non-Gaussian than the vacuum fluctuations. So with this, maybe I'd like to conclude, and I hope I have been able to convince you that gravitational waves are essential to probe any 3D combination physics. I've also shown that vacuum fluctuations are a proof of the quantum nature of gravity. They are crucial to prove inflation, and they are weakly non-Gaussian. And finally, with the help of an explicit model, we also managed to show that the sourced gravitational waves can be highly non-Gaussian, and thus non-Gaussianity of the primordial gravitational waves is an important test of their origin. Thank you.
So for today, we are measuring the high spectrum for different configurations. So we can possibly constrain this. I think you have 2 parameters.
Yeah.
So gauge density, source density, and this coupling strength.
Yeah, you can. I mean, I actually do show it, but we do that. For instance, here. So yeah, FNL tensor is essentially something that actually Planck also measures. And this is the energy density or spectator of this gauge field, and this is the coupling strength of this gauge field. And in this parameter space, some part is already excluded by measurements from Planck already. And let's say if we can reduce it down to this level where we measure the tensor FNL to order 1, we can rule out all this parameter space.
What would be the expectation for like a
Yeah, so
light
for,
cloud or
for light mode, this is in fact the expectation. So FNL tensor of order 1.
question?
So mostly you consider non-Gaussianity. If the universe has a primordial anisotropy, can you apply similar argument? For the vector inflation may predict the anisotropy expansion.
I mean, I guess there you would still be able to distinguish using non-Gaussianity as a probe.
But my understanding is like a non-Gaussianity and static anisotropy difference too.
Yeah, exactly. That's why you could potentially, even in that case, use non-Gaussianity to distinguish. But of course, the formalism probably changes because for vacuum fluctuations, I always assume a homogeneous background.
Right.
Yeah, in this. Yeah. So we need to calculate what is exactly the signal for that kind of information.
So you assume there's some pseudo-scalar field, like action. There are already some kind of constraints on parameter space for action itself.
Yeah.
So is there any implication? Because action is now considered to be very exciting candidate for even dark matter.
So that is actually a bit unclear because this axion might not exactly be the QCD axion or the dark matter axion because the energy scales are so different. So any constraints that we have from all these ground-based experiments might not actually apply to this era. So I mean the only hope is to use this kind of analysis to constrain axioms in that era.
Can we some different, just a different type of pseudo-scalar field?
Yeah. Because again, the era of heating is not clear, so we don't know how the axion field that was present during inflation behaves after inflation ends.
Any other questions? I'm not sure if the T is ready. Let me finish. Okay, that's somewhere. Okay, so if you have further questions, please thank Aniket again for